of the software. Thank you. Ram is chief of the Software and Systems Division at the International Technology Laboratory at NIST. Prior to joining NIST, he was an engineer faculty at MIT and helped set up the Intelligent Engineering Systems Laboratory. He has a Bachelor in Technology from IIT Madras in India and a Master's and PhD from Carnegie Mellon in Pittsburgh. He has co-authored or authored more than 275 publications, and as of this morning, he's an H-index of 54 with over 10,000 citations. And he's a fellow at ASME, AAAS, IEEE, SMA, and the Washington Academy of Sciences, as well as a distinguished member of the ACM and senior member at AAAI. He's received several awards, including the NSF's Presidential Young Investigator Award. He's in the Washington National Academy of Sciences, and he's received a Distinguished Career in Engineering Sciences Award. And he has an ASME CIE Division's Lifetime Achievement Award. So with that, I'll let you take it away, Ram.
Thank you very much, Keith. Again, it's a pleasure to give this talk. I used to come there now and then. I really enjoy my trip to ISI. This talk that I'm giving is entitled Explorations in AI, a Personal Journey. So I'm going to give my journey of what happened to me in the last 4 decades of working in AI. Some of the slides that you see are kind of introductory in nature, so I'm going to skip them because this is based on a talk that I gave at USC main campus for the undergraduate students. So I'm going to do a very brief introduction to NIST, a briefer introduction to AI, I guess, or a brief introduction to AI. I'll talk about AI at NIST, and then rest of the time I spend talking about my journey in AI. So NIST, you can go to that website at www.nist.gov, and essentially the main purpose of the mission here is to promote US innovation and industrial competitiveness. And there are three items there: measurement, science, standards, and technology. And the idea is to improve and enhance economic security and quality of life in the United States, but we also kind of work with other nations too. So measurement, science, and standards are the key aspects of NIST mission. In terms of the AI, I'm not going to go too much into what intelligence is all about, because you have your own notions of what intelligence is. But one thing I would like to point out is that there are various attributes associated with intelligence. It's not just problem solving. It's a number of other things that one needs to do with it. You can see here are some of the attributes of intelligence. In addition to these attributes of this intelligence, you also have this notion of awareness and consciousness, aesthetic appreciation, emotion, sensory acuteness, and muscular coordination. So there was a nice book by Howard Gardner who talks about this theory of multiple intelligences. So in other words, intelligence is only not on a single dimension, but intelligence is multiple dimensions around here. So you talk about aesthetic appreciation. Some people are very good at music, and so that's also an intelligence part of it. So there are different dimensions to intelligence, not a single dimension. And so when you think of making computers more intelligent, you also have to think about these kinds of these dimensions too. So this is one of the this is a traditional view of what an AI-based system is all about. There's an intelligent agent, and the intelligent agent is communicating with the environment, and there's a perception where there are sensors where you're getting signals from the outside world, and based on the signals and based on some other prior knowledge, you're going to make some decisions, and then you're going to take some actions, and those actions can be done through manipulators in terms of robots. So in terms of a brief history of the evolution of AI, I kind of have several stages here. One I call the prehistory, and that's the Paleolithic and the Neolithic times. I just use those terms just like that, but nothing importance except for the fact that in Paleolithic, we are talking about 2,000, 4,000 years ago, where the Indian and the Greek philosophers actually did do a lot of work on how the mind works. They did, the Indian philosophers looked into the way you represent knowledge, and people talk about ontologies and so on right now. All these things they were using, and they also had different kinds of inferences like analogy, case-based reasoning, and regular deduction, and so on. So if you look at some of the Indian philosophies like Nyaya Sastra, you see all these are well documented. Then you also have Greek philosophies like Aristotle's syllogism, where he talked about like deduction. Socrates is a man, all men are mortal, so Socrates is mortal, and those kinds of deductive inferences they did. And then you have in the Neolithic period, I call it, where you have Hume, Russell, Turing, and a host of people. And Turing is the most advanced of them all. And you know about the Turing machine, where he contemplated how machines can be as made intelligent like human beings, and what does it mean by a machine being intelligent. Then you have the beginnings where the term AI was coined. Then we have the early years of AI and the rise of knowledge-based systems. And this kind of lasted for almost 23 years with the general problem solver from CMU, Dendrel from Stanford, Hearsay, speech understanding system from CMU, Maxima from MIT, and Mycin for infectious diseases consultant, and a whole lot of things you can see there. Shidlu, Shaky, etc. I think Shaky was from SRI/Stanford. Then you have this whole notion thing called knowledge is power. And that's the one which Edmund Feigenbaum popularized in his book also. We also saw the rise of the early neural networks. And this is called the first wave or the first revolution of AI. And this lasted for about 10 years. And for many of you who worked in the 1980s, there was a lot of not only interest, there's a lot of demand for people who could do knowledge engineering. And the salaries were pretty high at that time too for these people. There's also the work on early neural networks going on. In fact, I think Jeff Hinton was at Carnegie Mellon University at the time. He was a Turing Award winner recently, and he used to work on these neural networks. But not that much importance was given to neural networks. Then there was this notion of silent period, where actually things were happening in AI, but there was not much noise made outside. So you can see that things like Deep Blue on chess, the rise of the robots in the industrial world, and you have seen a commercialization of the speech technologies. For example, naturally speaking Dragon and a host of speech technologies were actually being used in the commercial world. Then from about 2000 to 2015, I mean, these are all approximate dates, and you probably have your own dates too. Neural networks came to the fore because of GPUs, CPUs, and computing becoming cheaper and cheaper and more efficient and more powerful. And this people call the second wave, or the second revolution. And because you could have multiple layers of neural networks, this was known also as deep learning. So learning was an important aspect of it. And some of the tasks like image classification, classification was one of the most important tasks around here. Then I think around 2015, we are seeing what is known as the symbiosis of neural networks and knowledge networks. We'll come to that later on. We have these notions of explainable AI, open knowledge networks. So this is the third revolution, where the idea is to combine both good aspects of neural networks and knowledge networks, their advantages and disadvantages of each of these, and we'll come to that. And I think finally, you'll see what is known as the conscious machine, that is artificial intelligence having consciousness. And there was a book by Susan Schneider called Artificial You, AI and the Future of Your Mind. And she talks a lot about this aspect of it. Then for those of you who actually are interested in the history of AI, Henry Couts in the AAAI talk, AAAI gave a very nice and interesting talk on the history of AI. And that and this URL here as a link to his talks and his slides. These are some of the topics in AI people normally work on: knowledge representation, inference, machine learning, perception, and robotics. And this is a slide again you must have seen. of how you classify all these things, where AI is the big thing. Normally you see AI, machine learning, neural networks, and deep learning, and I put knowledge systems in there because I think knowledge networks are going to play a major role in the next aspects of AI. So that's the reason why I inserted there. Again, this I'm not going to go into details, except that you can see in terms of machine learning models, there are people who take features, and from features, you learn new features, and all these models are built on a notion of a feature. And then you have raw data, like in neural networks, where you take raw data and that's somehow converted into some symbolic structure at the end, where you have input layers and output layer is some classification. This is something to do, and deep learning is used all over the place. Again, I don't want to go into too much details because most of you probably are familiar with this. So this is what the state of the art of neural networks. You have something like imaging network doing classification, and the system kind of learns a function. And one of the things that these systems don't do very well is why did you do that? Why not something else? When did you succeed? When did you fail? And what potential errors are there? So those are the kinds of things the neural networks are not really good at. They're getting there, but not very good. There are problems. And this slide kind of shows you in terms of learning performance, explainability, and the neural networks. And many of the learning, the neural networks are good at, in terms of the classification tasks, they're very good in their performance. But however, in terms of explainability, they're not very good. And knowledge networks and decision trees are very good in explaining, but their performance is on some tasks, not every task, because there are a range of tasks that you're doing generally from diagnosis to design. They're not neural networks, although the new generation called the generative adversarial networks are coming into picture. They're not as good as what the symbolic systems can do for design purposes. On the other hand, for classification purposes, they're very good. So you have to keep that in mind. Okay, and these are some of the things that I did. Again, as I said, this is my personal journey. In 1986, I started this journal called Artificial Intelligence for Engineering. And I think later on, during the 1990s, when AI was not as big, this publisher renamed the journal to Advanced Engineering Informatics and sold it to Elsevier. In 1992, Chris Tong and I did a workshop at a AAAI on AI and design, and the output of that is this 3-volume series on artificial intelligence in engineering design. And I think a lot of articles in that book are still valid right now. Then I used to teach a course at MIT. After CMU, I went to MIT, so I used to teach a course on intelligent knowledge-based expert systems for engineering. And based on that, I wrote this book called Intelligent Systems for Engineering, and it came out in 1997. So briefly, in terms of the AI at NIST, about last February or so, there was an executive order by the president, and there was, you can get that from, there's a URL there, and you can download the report. And there was a big push for AI, and what the report explicitly pointed out is that it calls for the National Institute of Standards and Technology, NIST, to lead the development of appropriate technical standards for reliable, robust, trustworthy, secure, portable, and interoperable AI systems. So really, the focus is on trustworthy AI. When we talk about AI, we talk about people using AI systems for decision making. So how do you trust this AI is a key question. So in terms of NIST, we actually use AI for some of the metrological things that NIST, because metrology is really standards. So how can you use artificial intelligence to do better measurement science? And similarly, how can you use the measurement technologies developed at NIST for AI? So that is, how can you measure AI systems? Just like you measure, just like you have units, kilogram, centimeters, and meters, and so on. Similarly, and then you can measure that physical unit as physical system. Can you do the same thing for software systems? Can you have a set of measurements so that you can determine whether this particular system is good on a particular dimension? So the dimensions could be reliability, explainability, security, privacy, and those kinds of things. And we also do, we also have a lot of applications which we use AI for material science, smart manufacturing, and biomedical imaging. So we have AI for NIST and NIST for AI. That is, we use artificial intelligence for the measurement science that we do, and we also try to work on measurement science for artificial intelligence and to do with trustworthy AI. So there was a NIST-produced plan which talks about the US leadership in AI, and on a record time, Elham Tabasi and the colleagues put together this plan, which you could download it. This is based on a number of workshops and input from external agencies too. So this has about 3 parts: AI and standards, priorities, and recommendations. And one of the things that NIST is doing is organizing a series of workshops. And the first workshop is going to be, I think, sometime August 4th or 6th, one of those things. I'm sorry, the second one is going to be on August 18th. So you can go to that website, www.nist.gov, topics in AI, and you can go and register for these workshops. So these are some of the things that NIST is doing in AI. As I mentioned before, that we do AI for NIST and NIST for AI. And here is an URL, which is http nist.gov topic/artificial intelligence. If you go to that URL, you can see all the projects that are going on in AI at NIST. So much, there's a brief introduction to AI and brief introduction to NIST. Now I'll talk about some of the activities that I have been involved in, starting with the rise of the expert systems. And here is my journey, starting from 1981 to now. Initially, I'll talk about the projects that we did early on in 1981 or so, to my PhD thesis, to the work I did at MIT. From there, I went to NIST and so on, okay? So in terms of in the early 1981 or so, we started this project. And let me briefly explain what this is all about. You can see a model of a knowledge-based expert system at that time, where you have this knowledge base in where you have rules, frames, and logic as the representation scheme. And then this inference mechanism around here, which is backward chaining, forward chaining, constraint propagation, hierarchical generate and test, truth maintenance, and a whole lot of things in there. You have the short-term memory, which is the context. So this is the model that was used at that time. So what happened is about 81 or so, Westinghouse Corporation came to Carnegie Mellon University and said, we have a problem. The problem we have is that at that time, Westinghouse used to manufacture these things, they used to call it people movers. Actually, people movers are those train-like systems. When you go to an airport, these are totally automated. You go in and this train takes you from, or at least moves you from one terminal to another terminal. So they were having problems with this. One of the problems is that if you look at those doors were opening midway through, and sometimes the doors were not closing when they're supposed to close, and so on. So there are a number of diagnostic problems they were having with the doors. So they came to us and said that, well, can you develop an expert system for this thing? Because expert systems were pretty popular at that time. So I was in the Department of Civil Engineering. For some reason, they thought it was transportation. So I gave it to the Civil Engineering Department. But actually, it's nothing to do with transportation. It was more to do with model-based diagnosis kind of things, because it's mostly circuit boards and those kinds of things. So we had to learn a lot about electrical circuit boards and how things communicate with one another. And we actually ended up developing a model-based hierarchical diagnostic system, except that we couldn't publish because this was some contractual agreement with Westinghouse. We used a system called a CAS, which is a knowledge acquisition system developed at SRI, which was based on another system called Prospector. And for those of you who go back about 40 years, you probably have heard of this system called Prospector. And Prospector actually had a very, very, very nice domain-independent expert system that's called CAS in it, except that occasionally it used to ask questions about geology, like rocks and so on, but that's okay. That's a little errors here and there, but otherwise it was a pretty good system. So we developed the first version in 1982, and then we used another system called PDS, which was developed at CMU, which took the sensor data in and did the diagnosis. So this was a pretty good experience with that. There were several hundred rules in there, and the knowledge acquisition process was very interesting, because initially the Westinghouse engineers were very, very reluctant to give their knowledge to us, because they thought they were going to lose their jobs. But eventually we had to explain to them we were just doing this as a project, and we had to become friends with them before they give us a detailed knowledge of how they solve these problems. Then from diagnosis, I went into design. I did my PhD, which I completed in 1986, and this was in system which was based, excuse me, so it was a integrated design system. Actually, it was named Destiny because it's your integrated structural design system, and I thought it was my destiny. So I named it that way. And this system was based on, it was modeled on hearsay 2. At the time, Raj Reddy had developed hearsay 2, which was, I think, one of the first speech understanding systems, which actually one of the speech recognition systems which could recognize connected speech. Harpy and hearsay. Harpy came first, and then hearsay 2 came next. And they developed this thing called it was a blackboard model. So what hearsay really did was it did signal to symbol. So Raj kind of gave me this hearsay system and said, well, you might want to try this for design. And then Steve Fenves was my PhD advisor, and I talked to Steve Fenves. He said, yeah, that might be a good idea, talking for design, because in design, what happens is you also have several knowledge sources, knowledge experts like an analyst, or people who can do CAD, people who can do tolerancing and so on. So you have a host of people, number of experts, and they kind of collaborate in a way. So we developed this. We developed this entire. I re-engineered the hearsay 2 so that it could be used for top-down processing rather than bottom-up. As I said, hearsay was going for signal to symbol, and they did some symbol to signal, both top-down and bottom-up they had, but it was preliminary to go for the speech of sonograms, the speech signals, and from the speech signals, you somehow managed to get into words from words to sentences and so on. So here we go from requirements, from the top level requirements, you do the design, where bottom level are basically your design components in civil engineering structures, beams and columns, and if you have HVAC systems and so on. So this is how the architecture of the system kind of look like, very similar to hearsay 2. So when I finished my PhD at Carnegie Mellon University, after writing my thesis, I published it as a book called Knowledge-Based Approaches for Structural Design. And we also did something which is, as a part of this, we developed a domain-independent design system. Just like in CAS, you can put in diagnostic knowledge. In the system that we developed for design, you can put design knowledge, because in design, we have notion of goals, constraints, and those kinds of things. So you have to incorporate them rather than backward chaining kind of rules. We have rule systems also in there, but the rule system is part of this, this entire framework. So we ended up developing a domain-independent knowledge-based expert system. So then I went to MIT to teach in the Department of Civil Engineering as assistant professor. And there, what we did was that then I looked back into how the whole design process works. So here is an example where you go from actually customer specifications. This is this one, customer specifications have to be mapped onto engineering specifications, and then you put it on the internet. Internet was just about coming up at that time. So people were not very sure, especially in the engineering world, what do you do with internet? Everyone thought it was like AOL.com. But then we kind of hypothesized, because I came from CMU and I was kind of talking with all the stalwarts at the time, I kind of realized that internet is the way to go. So in here, what we do is that we put this into a thing called Design Evolution Database. This is a database management system, which is very different than traditional databases. There is a workflow. And the first step is this notion of mapping this engineering specifications to a conceptual design. And that's a knowledge-based activity. And now what I'm going to do is to run a short video, but this video was kind of produced in 1990 by Alan Mullally, who was the chief engineer for Boeing 777. And here is what he said about the knowledge-based systems at that time in 1990.
Now, computers don't design airplanes. We have not put the knowledge that's in the airplane designer's head into artificial intelligence that balances all these objectives. Someday, we'll continue to probably move to that end, but right now, the knowledge to design airplanes is in the designer's head.
So this was about almost 30 years ago, 1990. And now for many, I'm sure that many of you are working in the design area. Can I think about it? What's the state of the art right now? So while you're doing that, you kind of get knowledge from design repositories, because right now, many of the companies are multinational, so the knowledge will be dispersed across the world. And actually, there was a gentleman, Peter Will, at USC ISI about 20 years ago. So he had this similar notions where he talked about these design repositories and bits and pieces of the design, and how the designer can actually combine them together into a design, and then you can do the manufacturing part of it. The ideas are still vision ideas right now, okay? And he had some really, really nice ideas on how to do this kind of things. For those of you know, many of you may know Peter Will. He was a visionary at his time. Then we had this traditional CAD systems like AutoCAD. Now we have a Pro Engineer system, and then you have STRCs, and there's a whole Unigraphics. A number of CAD systems which are in the market, SolidWorks, and these things essentially do only geometry. That's why they're called traditional CAD. You go there and you draw the geometry of, you draw the, if you are designing a gear system or whatever it is, you draw the, you do a geometric modeling on that. Then you do an analysis. Analysis is generally done, in a finite element analysis is what people use. Then you have this whole notion of virtual prototyping, where you can put actually behavior into the system. And the system, when I drop something, the system actually does the physical simulation of that in silico. Then what I thought at the time, this slide set was prepared around 1994 after I went to NIST. What I thought at the time is that we could potentially, there is two of the most widely used applications of computers are video games and word processing systems. So I thought virtual reality is something which will take over. So augmented CAD is something where you have a close binding between the silicon and the carbon. So there's a carbon silicon interface around here. So virtual reality may be something where people will become popular in the engineering world, although it became very popular in the game world. And now we can see distributed games being very popular with the teenagers. So then you have, this is just the design network. Then you have the manufacturing network and so on. So there are different kinds of networks which are coming in. So there are a lot of issues around with this thing that one needs to develop on. I'm not going to go into details, but this provides a framework for the DICE project, which I'm going to talk about next. So in terms of the computer-aided design, there are I told you the human is sitting in front of a computer and trying to do the design, and this is true for a number of other applications, including healthcare. The first part is you got to input into the system. Now at that time, as I said, that mostly used to be geometric models. Now, of course, there are things like sketching and maybe hand waving and those kinds of things. There's a gentleman, Karthik Ramani at Purdue University. He talks about, he does this virtual sketching. And there's also some work going on in your University of Southern California in your mechanical engineering department from SK Gupta and folks. So they're all kind of doing these things. Then the next step is the storing part of it. So when you generate this design, like for example, if you look at Boeing 777, it's supposed to last about 80 years. Similarly, as human beings, we're supposed to last for 80 years. The question is, how do you represent this information or knowledge? And not only representing knowledge, the knowledge has to be persistent across the 80 years or so. So there's a number of issues involved in that. Then you have solutions you have to solve. And in terms of the solution, you do analysis, you do modeling, decision-making, simulation, and a whole lot of things. Then you manipulate your CAD models are actually models in the system where you can do searching, mining, you can create new knowledge. And also now we are talking about these are heterogeneous systems. They have to interoperate with one another. So you have design, and the design knowledge has to go to the manufacturing knowledge. And I think Steve Ray is here. He used to work on this mapping. He has developed something called process specification. Actually, he was one of the leaders of this process specification language at NIST, where you can represent process plans. So then you have knowledge from the information from design, which has to be transferred to the manufacturing world. Security plays a big role. And as you go through this process, what is the interesting thing about this whole thing is that there are different kinds of representation scheme as you go through this entire product life cycle. You have, in the initial part, represent things in terms of linguistic terms. Then you have pictorial terms. Then you have this symbolic structures evolving, especially in the concept design stage. These are ontologies. Then as you go to the analysis stage, you do algorithms and you do a lot of mathematical analysis part of it. Then you go, once you do a detailed design, the number of representational schemes. And then after that, you go back into manufacturing. Then you have both linguistic and symbolic schemes coming into the picture. So in other words, there are multiple knowledge representational schemes that needs to be encoded. Okay, so at MIT, when I was in MIT, I worked in the domain of civil engineering. I'm going to skip this video, which you can see later on. It shows how the system works. But we developed a system called DICE. This is distributed and integrated computer engineering system. And I named it DICE because people told me at the time this is a gamble. And I said, okay, and I named it as DICE. So DICE actually did something. It was started in 1986 and went until 1994. And it was essentially like a Facebook-like system for engineers. At the lowest level of this distributed object-oriented database management system, we used a combination of object store and Exodus. Over it, we built this thing called Cosmos, which is actually C++ based object-oriented rule-based system, which had both the Reti network that does the forward chaining and some probabilistic reasoning, which was incorporated in the cache system, likelihood ratios and those kinds of things. And it also had a C++ is basically a static language. So we had to develop a dynamic interface over C++ so we can evolve objects over time. Then over that, we developed this knowledge representation scheme called shared. We had a non-manifold geometric engine, which dealt not only with solid modeling, and not only with lines and planes and solids, but also with qualitative geometry. Like when you place things in a building in a particular place, you don't need to have precise location. It knows that it is on a particular slab. So there's a whole field called qualitative geometry, QRS, qualitative geometric reasoning systems, and we use that. Then we developed this massive constraint management system, which in engineering, you have all these objects related to other objects and their numerical values, and both symbolic and numerical values, they're connected to one another. So you can do manipulations on that when you call it ConMan, constraint management system. And ConGen is again re-implementation of the work I did at CMU. We did top-down refinement and so on. It's a domain-independent shell for doing engineering design. And over that, we had the shared DRIMS, which is a conflict management. So this is a massive system built by several graduate students over 10 years. So there's a lot of contributions that was done here. And many of these things were used, saw their light in the industry. I was working for Entity Data, was supporting some of this research. So many of these concepts, they took it back. And also some of the commercial CAD systems in the United States were looking into it. Then at the same time, I came up with this idea called comprehensive knowledge base for engineering. And the idea is that it's very similar to the open knowledge networks thing. And the hypothesis was that unless you build this massive knowledge base of engineering concepts, you really won't be doing anything useful in terms of common sense reasoning. There was psych, but psych was too big for engineering problem solving. So in engineering, there are certain terms like torsion, force, Young's modulus, and so on. So if you can just only incorporate knowledge of these particular units and how they're connected to that and create knowledge networks, then you can learn based on that. And this was built in a layered manner. And I left and joined NIST in 1994. And what happened is that all this stuff that I did on DICE came up in a book called, which is shown there. And if anyone wants a copy, just send me an email. I'll send you a PDF version. Then in 1994, I went to NIST and started and continuing my work on knowledge representation. And what we essentially ended up doing is that we said that now you got to represent form, function, and behavior so they, again, as I have said before, the number of representational, it's a multimodal representation scheme, not only diagrams, but also you need to represent things like form, functional flow, behavior, and all kinds of things. So we came up with this model called the core product model. And core product model has this notion called artifact, and artifact consists of a number of features, and artifact has function, flow, and and form as materials, geometry, all kinds of things. Again, I don't have time to go into details, but this kind of structure exists. And you have a notion of port for doing with electromechanical devices. Based on CPM, we developed an open assembly model, and open assembly model dealt with things like assembly features, tolerances, and a host of other kinds of things that are generally required in electromechanical systems. There's an example. I don't have time to go through this example. As I said, that I gave you, the slides are available, so you can look at this thing. And the key thing around here is that if you see this particular thing, there are artifacts, and artifacts have associations. So you can see the inklings of knowledge networks around here. This is really a knowledge network in the mechanical engineering world. So these knowledge networks were created, and you could potentially manipulate them. And then this thing got expanded. We could use it for analysis, the platforms-based design rationale, and so on. And people actually took this thing and applied it to, expanded it. Like, for example, Georgia Tech for design analysis integration, Arizona State extended features, Wisconsin Madison did it for heterogeneous material modeling, Syracuse for tolerance and kinematics, and at the time S.K. Gupta was at University of Maryland and used it for assembly-based search. So I'm gonna skip the next few slides, except that we had to go from products to processes. As I told you that Steve at the time was working on this thing called process specification language with Michael Gruninger, and then Steve became the division chief, and Michael Gruninger took over it and developed this thing called process specification language, which became an ISO standard. So you can Google it and look at the details. So now in the next 20 minutes or so, I'm going to talk about things that are happening from 2010, where I took over as the chief of the software and systems division at NIST. So the number of projects that we are working on concerned with AI, and as I said, one is the AI for metrology, and I'm not there, and each of the slides have a goal, use, and impact. I'm going to go through some of these examples, and the people who are primary people who are here, I have this in the slides, so I can contact them if you need more details. The AI for metrology is using AI for measurements. I'll show some examples later on, so I'm going to go fast on these things. And the next one is AI for image processing, but in this case, it's also related to the previous attempt, Thrust, except for the fact that then this one uses high performance computing like GPUs and CPUs to do image analysis. Then we have natural language processing for question and answering, and this is to deal with the materials genome initiative that we have, where we scan through large volumes of text and extract the appropriate information. We also have developed something called the root and rule-based technique, when I'll talk briefly about that later on. And this uses a combination of neural networks and a technique called root and rule-based technique for doing both search, creating taxonomies, and document clustering. Come to that a little bit later on. We used a machine learning technique for extract protein-protein interactions from text. Then the other interesting project is using AI for bug finding. This is a pretty interesting project and evolving. And the idea is that if you look at software has many bugs. And how can you use artificial intelligence so you can detect these bugs? And there are a number of issues involved with this particular project, and Paul Black and Vadim Okum are leading this. So now I'm going to talk about a few projects in terms of what we are doing right now. I'm going to take about next 20 minutes or so on these things. So there are a lot of projects that we are doing at, as I said, I'm going to go through some of these things pretty fast, but I'm leaving the slides with you, and you can go through it. And if you have any questions, you can come back to me. So again, the idea here is to develop test methods to evaluate various imaging algorithms. And there are a number of other things which we do with imaging, which are not relevant to AI. So I'm just going to skip the rest of the things, except go through two examples around here. One, like many of you, I mean, the older generation, actually, if you have heartburn or something like that, you go to a doctor, and the doctor puts an endoscope in your esophagus and kind of detects all kinds of anomalies in that particular tract. And then if you have a problem at the rear end, this is the input-output system. So if you have some problems at the output end, they put a colonoscope and then try to detect some polyps, and the polyps eventually become cancerous. So this takes a long time, about 10, 15 years. That's why they ask you to do colonoscopes when you're about 50 years or so, because a number of genes have to be mutated. But then what happens is that when you talk about this, there's nothing which goes into the small intestine. And for that, what they have done is that they've developed this thing, given imaging, a smart pill. And what you do is that you take this particular pill, you swallow the pill, and the pill kind of takes, keeps taking videos as it traverses the small intestine. It takes about, typically about 8 hours or so of video. And what the main problem with this video is that, let me go back to the next slide. This is how the video is taken, and this is how it kind of looks like. So the doctor actually has to go through this 8 hours. So we decided that why can't we automate this process? So what you can do is that you can take the images in the system, and you can actually identify where the potential problem is and what kind of a problem is that. So here is what we did. We took all these images, and along with the doctors who identified some of the features around here, we could potentially and then use machine learning algorithms so that we can generalize these things. And these features can then be mapped into ontologies, which was developed by, we had a doctor working with her, Mala Ramaya. She developed this ontologies for the GI system, and you can map that into these ontologies. For example, if you have the features that you have can be mapped onto this Crohn's disease features, which is essentially idiopathic inflammatory bowel disease, or you could have ulcerative colitis, which is the same as this thing. So one has to believe this. I mean, this is a prototype, and we didn't continue after that for several reasons. But anyway, one can do these kinds of things. So you can use some machine learning algorithms, extract some features, and map that into ontologies. One of the biggest projects we have right now is this CS metrology for image processing. And this is led by Peter Bacci. And the way that this one works is that you have the biological metrology and you have the computational science. So biologists, like for example, our sister division, laboratory, the materials measurement laboratory, they are constantly working on biological systems. And here in this case is that there are microscopes, and these microscopes are looking into petri dishes and taking images of the petri dish, of the cells which are in there. And these cells are actually live cells. They keep growing. And then these images they take, and what happens is that these images are taken over several months, and you have to scan this entire petri dish, and you essentially end up generating gigabytes to petabytes of memory, depending on of data, depending on what you are doing. And what they do is that they send us the raw images, and we do all the stitching, image stitching, and so on. Then we do the segmentation and develop feature extraction, and they look at it and they see if it's okay or not. So it's an iterative process between the biologists and the computer scientists, and then we develop the machine learning algorithms kind of learn these features, and then they can be used to actually do and actually they kind of give you confidence in the measurements that the biologists are taking. So here is an example of the system in action for macular degeneration. One of the problems with macular degeneration is many of us have this macular degeneration gene. Some it may be expressed and some it may not be expressed at all. And the global cost is about $340 billion or so, and 11 million people in US suffer for that. And the thing here is that for people who have macular degeneration, that's what you see on the top here, a blurred vision, and we want a 20/20 vision. For that, what you can do is that you can take the blood from an individual, and then you can get the pluripotent stem cells from there, and then you can modify it so that these stem cells, they become cells which can be transplanted in epithelial cells, which can be transformed into the epithelium of this of the eye, or the retina of the eye, and then you can grow these things. But all colonies are do not actually end up to be potentially good candidates for transplantation. Only some colonies tend to do good and some colonies don't do well. So in this case here, we are gathering this data 6 to 9 months for each candidate, and you can have several patients in there. And then once you determine if there is a particular colony which is going to be good, then you take that colony and then you inject it into the eye. And then, then people will get this kind of vision. So we're working closely with NIH on that. And this is the system that there are a lot of problems associated with it in terms of scale, complexity, speed, and so on. And there is a system at NIST, and the URL is here. This system is called WIPP. It was developed by Peter Bacci and his group. And it's a very complex system. And actually, one of the things you can do is that you can actually go through this petabytes of data, and you can even extract some of it and do at the client. Here you can see you can do analysis on the client, or you can do analysis at the client level, or you can do at the server level. And then you have all this machine learning and neural networks kind of things, which actually have done the feature recognition and so on. The feature extraction is done, but sometimes you have to do context-based enhancements to these things, which is segmentation, tracking, and prediction modeling. For sometimes you may not get the actual, sometimes you may have in a situation where you don't have enough images. So what you do is that you use GANs to generate this simulated images, and then you feed it back to the neural networks. The other thing that Peter and people have been working in is explainability. How do you generate rules from neural networks? And here is an example with which the biologists were doing, identifying various components of a cell. And you use Raman spectroscopy, microspectroscopy to do that, and these are the signals. And what happens is each one of these components of the cell has a particular signal, and based on that you can identify what this is, like a nucleus or a cytosol, lipids or minerals. So what Peter and his people did was that using these neural networks, they extracted the rules, which are something, this is the reference rule which the experts kind of give you based on the Raman spectroscopy that you have seen there. And these are the rules which are generated by their system. And this is the rule for a nucleus. You have 3 different rules, with you can add a number of rules, I guess, for a particular component. And this is the kind of thing that they have extracted based on this reference model. Okay, then you can, the other project that one of the issues with neural networks is that how do you know what approach you have to follow? And this particular project kind of looked at various approaches to determine which is an appropriate approach to follow. I'm going to skip through these slides, interest of time, and go through the next one, which talks about taking natural language processing system. Now what happens is that many of the systems, languages like Sanskrit and many European languages are written languages. And what you can do is that you can form compound words, noun words. For example, policeman in English is kind of interesting. You can create policeman, not a police dog, as one word. So, but these languages, you can do those concatenations, and there are a number of rules that you use to do this concatenation. And that is the technique that we have used, and it was based on this Panini's grammar, which was originally in Sanskrit. So the idea is that you go through the particular paragraph, let us say, and you see something called an inertial frame of reference, you can condense that into a simple thing called initial reference frame. So these are the 3 words in there. And there's a whole way of how you can do these things. Again, since I'm giving you an overview. So what you can do is that you can use this in search. For example, and this is a thing that we developed for the COVID-19 data set, where if you go to this COVID-19 data.nist.gov, okay, I think if I press there, I think it can come to this thing. There's a data repository. I don't know whether you can you see that? Probably not, I'm not sure. But if you can press that, I can see that here. I don't know whether you can see that or not. But what you can do is that you can do search in that. And you can search the database, like you can go to virus. And just like, when you do Google search, it will, this one also will fill up the terms that are nearer to this virus, in this case, virus specific immunity. And doing after that, you can get all the articles which are related to this particular search. Right now, we have more than about 190,000 articles in our data repository, and the system can go through that and give you the appropriate articles relevant to the research you are doing. And this is and people are using this outside to kind of do search over articles, because as you know, in the COVID-19 era, every day people are publishing articles on that. You can create taxonomies based on this technique, like here is a case in the diabetes world. And these taxonomies can again be used to create ontologies, and ontologies can be used to create knowledge networks. So we have a project which is doing that, essentially reading text or journal articles and create knowledge networks from there. And these things are very useful. In fact, Yolanda gave this talk in the AAAI presidential address where she talks about scientific discovery. And for scientific discovery, it's very important that you have a robust knowledge network which could be trusted. We got about 10 minutes to go. Again, as I said, we have this multiple multiple representational schemes that you need to have. And there is a representation scheme which was developed by the French probably about 50, 60 years ago, called category theory. Go back to engineering, people use Newtonian mechanics for representing and doing a simulation on that. Similarly, people use predicate calculus which is a language and technique for logic. And we believe that category theory is a technique which can be used to encode knowledge from various levels of abstraction. And then here you can see where you have things like taxonomies represented in XML to first order logic there, and category theory, using that, you may be able to span this entire spectrum. Again, we are doing some experiments on that. And one of the things about ontologies is that this ontology summit, which some of you have given talks in, an ontology summit, which I think originally was pioneered by Steve Ray at NIST, and then I took over after he left. And there were a number of people who organized the summits. That website, and you can see 10 years knowledge about ontologies. All of them are recorded there. And there's audio recording, there are slides. So for those of you working in the ontology world, I urge you to visit that. We also are working on this. One of the problems with neural networks, as you can see, is people can train it for something like here, guitar and penguin. And again, you can do slight changes in the image. And you can show this, you can give it these images, and it thinks this is a guitar, and it's a kind of this image is a penguin. Okay, all that nothing to do with penguins and guitars. So NIST is working on a project with IARPA, and the idea is the following. For example, here you have the stop sign, and if someone can insert something in there in this image, and it thinks it's a speed limit sign. So people can inject Trojans into these images. The question is that how do you detect that? How do you detect it's a Trojan? So IARPA as a program in doing this, and NIST is helping IARPA, and we work on about several aspects of this thing. So for those of you who are interested in this, there is a URL for that, pages.nist.gov/TrochAI, and that will tell you what exactly we're doing. But anyway, in summary, the thing is that when people develop methods to detect these Trojans in these images, how do you know these methods are good? How do you determine that they are accurate? So that's where we come in. We come in several aspects. One is that we actually have this reference data sets, and along with JHU, so APL, we develop these data sets which people can use when they develop their algorithms to see how robust the algorithms are. Then there are a number of algorithms which have been developed for detecting Trojans. So we do characterize these methods. And then we're also doing some fundamental research in this area. So there's a lot of stuff going on in that, and you can go through this to the website. And finally, as I'm taking about a couple of minutes to summarize here, Gary Marcus and Ernest Davis wrote this book called Rebooting AI. It's a very nice book where they talk about the limitations of the neural networks and how you need to have them combined together with symbolic structures such as knowledge networks. I don't know if they call it knowledge networks or not, but that's what they talk about in this book. It's a very, very nice book. And this whole concept of open knowledge networks came into picture. And this open knowledge network is again, NSF funded about 30 or 40 projects a year or two ago, I think last year.
Ram, just to interrupt briefly, just so you know, it's 12 o'clock. So
yeah, okay. So I'm going to now close, except that say that there is this OKNs which have their advantages and the neural networks which have their advantages. How do you combine these two things? And there's this whole notion called predictive coding, and using predictive coding. I'm just going to skip through the rest of this predictive coding, except say that now what we can do is that we can combine both the OKN type of knowledge and the neural network knowledge along with the sensory data. We can find out the errors because most of the learning happens because there are some errors in your predictions. So you can get those errors in your predictions and do machine learning. Again, this work is preliminary. And then again, I leave you with this thing. Take about 30 seconds to read this. And these are the kinds of things we want to solve in the future. And these kinds of articles always appear in things like New England Journal of Medicine and so on. So here you can see a case study where someone thought after doing initial analysis, they thought it was Crohn's disease, they eliminated Crohn's disease, but then doing after analysis after some time, they found out that it is indeed Crohn's disease. And you can see there's a lot of types of reasoning happening here, symbolic reasoning, deductive reasoning, some inferencing going on, and also some processing images which are there on the bottom of the screen. The idea is that when will you develop a system which can do these things? And this is in line with Yolanda Gill's talk at presidential talk at AAAI, where she talks about scientific discovery. So we need to advance in those areas. Okay. So anyway, that is the last slide. Actually, that's not the last slide, except that this one says you need to do bias-free AI systems. Testing algorithms will increase trust in AI. Standards are important. We have metrology for AI and AI for metrology. This talk is based on the work by several people at NIST. And also there's a standard disclaimer. Okay, thank you.
Great, thank you so much, Ram. In the interest of time, I do want to at least have one person be able to speak or ask a question. So does anyone have an important question that they want to ask? Feel free to raise your hand or to speak up.
You can always send me email. I think my email address is there, and we can always talk offline. I know I kind of exceeded a little bit, but then I had to cram 40 years of work in AI into 1 hour. So.
Oh, of course, it's always very, very difficult. All right. So yeah, I mean, I'll definitely be able to. I definitely have. Will love to learn more about your work, especially with the Trojan AI. So I actually went to the what do they call it? The workshop, I guess, where they sort of
The performance workshop you went
yeah,
to?
yeah. Where they introduced the idea of the two. There's Trojan AI and there's another one that they want to fund, and the Trojan AI was quite interesting. Do you have any initial results on that?
Pardon?
Do you have any initial results on?
Yeah. So that website that you have contains everything, and then it has a lot of information. And what I will do is that I will put, if you want, we can have a short video conference later on with the people who are actually developing that.
Oh, awesome. All right.
And if you go to the website, there's a lot of data sets and all kinds of things in there.
That sounds really
which
good.
you can download, and you actually can use those data sets if you're working in that area.
All right, great.
And also we can tie up some collaboration if you're interested with them.
Oh, absolutely. That sounds great. All right. So now that's probably a little over time for some people.